This is section 17, definite integrals graphically, example 3. So now that you know that the concept of a definite integral is nothing more than the area under the curve, we should consider a particular notation, and this notation has a very specific name, which you don't have to have memorized. You don't have to remember, oh, that's that function. You just have to know how to use it. Okay, so suppose we have f of x equals 2. And you can see over here on this graph that we have f of t equals 2. So x and t are kind of interchangeable, but we're going to be using t more than x just so we can see the difference between the original function and the final function. Now if I wanted to find the integral from 0 to x of f of t dt, then that would be finding the area under the curve starting at 0 and ending at x. So when I change the x value, I'm finding a new area under the curve. So for instance, if I go from 0 to x is 0, that's 0 to 0, which is just 0, right? We know that the integral from a number to itself is just 0. Then I have the integral from 0 to 1. So I need to find the area under this curve from 0 to 1, and that is 2. Now I'm going to find the integral under the curve from 0 to 2. So that's adding, right? That's adding another 2, so that's 4. Then 0 to 3, that's another 2. So that's 6. So my area is accumulating. Interesting. Right? And it'll keep going. So it'll be 8 and 10. It should be apparent that as x gets larger, the integral increases as well. We are accumulating area, and we call the expression from the integral from 0 to x of f of t dt the accumulation function. And again, you don't have to remember what it's called. You just simply have to know how to use it and how to read it and what to do with it when you get it. So now we have the function 2x, right? That is the output 0, 0, 1, 2, 2, 4, 3, 6, 4, 8, and it could have kept going. All right. Now we want to calculate the value of the accumulation function of this from 0 to 4. So let's find the area of this, area under this curve. When we do that, we get, the area from 0 to 0 is just 0. The area from 0 to 1, right, is 1 times 2 divided by 2, which is 1. From 0 to 2, that's this whole area, so 2 times 4 divided by 2, so that's 8 divided by 2, which is 4. 0 to 3 is 3 times 6, 18 over 2, which is 9. Interesting. Is this a pattern of some kind? 0 to 4 is 4 times 8 divided by 2, which is 16. Oh, hey, look. Let's graph this. We have the point 0, 0, 0, 1, I'm sorry, 1, 1. That's not right there. I'm going to use purple. 0, 0, 1, 1, 2, 4, 3, 9, 4, 16. If I plot those points, then we have an interesting function here. That ends up being a quadratic function. The quadratic function, x squared. Well, if I take the derivative of x squared, what do I get? 2x. Interesting. So if I take the derivative of an integral, I get the original function. This proves it, right? Because if I take this and I found the integral by finding the area under the curve, and then I took the derivative of that, it was undoing what I had just done. So now I want to find these values, okay? So let's first do the accumulation thing with this particular graph. So from 0 to 0, still 0. From 0 to 1, okay, so that's this area here. So we have 1 times 1 plus 3 divided by 2, which is 2. For 2, we're adding this area, which is 3. So 2 plus 3 is 5. Then we're adding this area. So it's 1 times 3 divided by 2. And for the sake of this problem, I'm going to go ahead and use decimals. So we get 6.5. For 4, this is below the x-axis. It's important. So we have 1 times 4 divided by 2, that's negative 2. Okay, so we have 6.5 minus 2, which is 4.5. That's really meant to be a 2. Negative 2. Which means this is also negative 2, right? Because that's the same area. So now we have 2.5. Now we have from 5 to 6, so 1 times 1 divided by 2 is 0.5. So we have 3. This area ends up being a quarter, so it's 0.25. So it's 3.25. And then this area is another 0.25, but it's negative, so we get 3 again. And then this area here is 1 times 1, that's 1. So, and it's negative. So that's just 2. Now we know that the derivative of the integral is just the original function. So if capital F of x is the integral from 0 to x of f of t dt, then capital F prime of x, when I take the derivative of that, I just get f of x. Which means that this table here, f prime, capital F prime, is just the values at those particular points. So all we have to do is go up to the function. So capital F prime of 0 is 1. For 1, we're at 3. For 2, we're at 3. It should take no time at all. For 3, we're at 0. 4 is down at negative 4. 5 is back at 0. 6 is at 1. 6.5 is at 0. 7 is at negative 1. And 8 is at negative